Okay, so we've already done this. This is just review. But for double integrals, right, if you're integrating some function of two variables, we learned how to convert that double integral into polar coordinates, right? So we use r and theta to describe things instead of x and y. But what we showed is if you want the same little differential areas, you have to actually throw in an extra r. When you switch from dx dy, then you go to r dr d theta. So it can mess with the integrand because you actually have to include other junk that shows up there. So if we're doing triple integrals, what we've been doing so far is you have some function of x, y, and z, and then we would have something like dx dy dz. So when you see the word cylindrical coordinates, it just means leave z the same, but then use polar coordinates to describe the x and the y parts of it. And so this would be some function of r and theta and z. And then you could use r dr dz d theta. It's probably the most common. Right, but you pick up the r because we're converting the x and y to polar. Okay, that's what we mean by cylindrical coordinates. If you have homework problems that say cylindrical coordinates, then it's basically just polar coordinates, but we're doing a triple integral, so you also get a z. Okay, more exciting is spherical coordinates. So I think we talked about spherical coordinates early in the semester. So all of this is like review stuff. If you want to convert from rectangular xyz coordinates to spherical, which is rho theta, and theta is the same angle as it is for polar coordinates, so that's nice and easy. And then phi is less obvious, so I'll try to show you what phi is. And again, we already did this, but I'll just remind you. Here's my 3D space. If I have some vector centered or with the base at the origin, the length of this vector is rho. So rho is just the distance from the origin. In other words, we could say that, I should be saying rho. Rho is equal to the square root of x squared plus y squared plus z squared. It's the distance from the origin. Okay, and then theta is what you would get if you took this vector in 3D space and you projected it down onto the xy plane, and then you ask what's the angle between the x-axis and the projection of that onto the xy plane. That's theta. Now, phi is the angle that this makes with the z-axis. And so we say that phi can be anywhere between 0 and pi. So if phi is 0, then you're talking about the direction that's pointed up along the z-axis. If phi is pi, then you're pointing down along the negative z-axis. And anywhere in between 0 and pi, phi is pointing farther and farther away from the positive z-axis. Okay. So that's a review of spherical coordinates. Spherical coordinates review. But the crazy thing is what happens to your order of integration, where if you have something like dx dy dz, or maybe you have dz dy dx, doesn't matter. If you've got a triple integral in terms of rectangular coordinates, you've got to replace this with now rho squared times sine of phi times d rho d phi d theta. So that's something you got to memorize for your next exam, is that you have to make that replacement every time you do a triple integral with spherical coordinates. I didn't want to draw this, and so I stole this from my textbook. But if you have some little differential volume in spherical coordinates, you can imagine taking this little chunk. It's like almost a cube shape, but not quite. Taking this little chunk out of the sphere, well, one of these sides is going to have side length delta rho, because that's just the change in the distance from the origin along that side. This side is going to have length delta phi, because that side length changes as you're taking a change in the angle away from the z-axis. But then also notice that if rho was larger, then that side length would be larger as well. And if rho is smaller and you're closer to the origin, then that side length would be smaller. So we also multiply that times whatever rho is. And this last side length, it, of course, mostly depends on what your delta theta is. That side length is going to be determined by this angle theta, or delta theta, as that changes your angle from the x-axis in the xy plane. But then it also depends on rho, because as your distance away from the origin grows, so is the side length, right? My radius of the sphere grows. And then the last thing is it also depends on what phi is, because if phi was really small and you were close to the z-axis, then that side length would be really tiny. And if phi is really large, when you get closer to the xy plane, closer to phi equals pi halves, then that becomes really large. And it turns out the sine function perfectly describes how this side length of this little differential dv chunk changes with respect to phi. And so if you multiply these together, like you would if you were taking the volume of like a rectangular prism, then we would have d rho as one of the side lengths times rho delta phi as the side length times rho sine phi delta theta, which is this side length. But if you make all the deltas into lowercase d's, and multiplication is commutative, so it doesn't matter the order in which you multiply things, then you can write something like this. Right? And so that's why if you want to convert from rectangular coordinates to spherical coordinates, you end up with a rho squared sine phi.
Would it be, instead of dr, would it be d rho?
Yeah, sorry. D rho. So you go to the ice cream shop in town, and you buy an ice cream cone. And they're going to give you an ice cream that has the bottom half of the ice cream contained in a cone, but then the top of the ice cream kind of gives you a little bit extra on top, right? They usually overfill the cone by a little bit. And so you want to calculate the volume of your ice cream. If your ice cream is this region in space, this is the equation for the cone, and this is the equation for the sphere that tells you how much ice cream is left on top. I want to graph this on GeoGebra. But GeoGebra is very picky, so I have to remember how to do this. I'm going to say, I'm going to rearrange this first equation to solve for z. So that means z is going to be equal to the square root of 16 over 9 times x squared plus y squared. That's only going to give me the top half of the cone, but that's fine because I don't want like a double cone, you know, like I don't want the full conic section, or whatever you'd call it, the quadric surface. I don't want the full quadric surface. I just want the top half of the cone for the shape. And then I'm going to rearrange this equation for the sphere so that z is equal to the square root of 25 minus x squared minus y squared. And hopefully this works out, and we'll see. Okay, I'm looking at square root 16 over 9 times x squared plus y squared. Aha. It's not as tall as I want it to be. I'm probably going to make that 9. There we go. Perfect, I think. So that's my cone part of my ice cream cone. And then the other one was square root of 25 minus x squared minus y squared. Okay, and that gives me the little bit on top. So imagine you go to your ice cream shop and you ask for an ice cream cone, and they give you that. So they fill up the cone with ice cream, and then there's a little bit on top following that sphere, okay?
They give you a diamond.
And so we're like, you know, what's the volume of this shape is what we're asking. Okay. So this is going to be a situation where spherical coordinates are going to come in real handy, because I can describe this stuff using spherical coordinates by saying let rho be anywhere from 0 up to the top sphere part of my cone. And one of my equations for conversion was rho squared is equal to x squared plus y squared plus z squared. So now if I look at the sphere, the equation of the sphere is just rho squared equals 25. I could just say rho equals 5. So sure enough, in spherical coordinates, it's really easy to describe a sphere. So I just say rho can be anywhere between 0 and 5. Now, theta can be anywhere between 0 and 2 pi, right? Because my whole ice cream cone is round. And then phi is the angle away from the z-axis. And so I have to think about like what a trace of my ice cream cone would look like. Where, let me call this like the xy plane, and then this would be the z-axis. So phi is this angle right here. And to get this angle, I have to use some kind of trig function. I think my conversion formula would tell you that cosine of phi, that would be the adjacent side over the hypotenuse of this triangle. And so the adjacent side is going to be some z value at the top of this section where the cone meets the sphere, you know? And then the hypotenuse here would be rho. But that angle phi, well, you know, you can start off at 0. 0 is in along the same direction as the z-axis. I'm trying to figure out what would be the maximum angle phi. And since this has the radial symmetry about the z-axis, that maximum angle of phi is going to be a constant. It doesn't deter, you know, it's not a function of theta, for example. It's just a constant number. And so really it's just going to be a mystery of figuring this out. And we've already said that the maximum value for rho is 5. And so I can replace this rho with a 5, because I know that's what the length is there. Where do I go next? So I need to know what the z value is. And I'm trying to think about how I can get that. It's really easy if I look at my graph, but I would like to come up with a neat way to figuring this out without graphing it. Because from my graph, it's really clear that this length would be 5, because that's rho. The height, I can just read off of this GeoGebra graph. The height where the cone meets the sphere is actually 4. And on the x or the y-axis, the radius of that is 3. So this is a 3, 4, 5 right triangle.
So what was it, 32?
I guess the way we would do this is we would say, where does that sphere intersect the cone? Obviously it intersects the cone at a circle. But if I could get the equation for that circle, then I could find out that the radius of that circle is 3, and that way I could solve it without needing to graph it first. Like if you were on an exam, obviously you can't use GeoGebra. So, okay. So our strategy would be to find the intersection of the cone which is 9z squared minus 16x squared minus 16y squared equals 0. That's my cone. And my sphere, which is x squared plus y squared plus z squared equals 25. So the intersection is going to happen when both of these equations are true. So maybe I can just multiply this equation times 16 and then add them together. So 9z squared plus 16z squared is going to give me 25z squared. Negative 16x squared plus 16x squared is going to be 0, and same with y. And then this is going to be 25 times 16. And so if I cancel out the 25s from both sides, z squared is equal to 16, which means z is equal to 4. So at the intersection between the sphere and the cone, this z value has to be equal to 4.
And then the other side will be minus 1.
Well, I don't care about z equals negative 4, because I'm only caring about the shape of this ice cream cone above the xy plane, you know? There could be like a mirror ice cream cone that lies below the xy plane, but I don't care about that one. You know, I only care about the top one. Yeah. Okay, so that means this z value has to be 4, and so this would be 4/5. And basically, cosine of my constant phi is 4/5, so that means phi is equal to arc cosine of 4/5, and that's not a very nice number. So we are doing well, but the question was asking what's the volume, and I know that I can find volumes by taking a triple integral and then just leaving my integrand as a 1. So let's do that. Triple integral, the integrand is a 1. Now, I have to decide on some kind of order of integration, and all my lower bounds and upper bounds are constants. So that's actually pretty nice. I don't have to worry about one and being a function of another one. Now I am going to pick up a rho squared and a sine of phi, because that's what you have to do if you convert from from rectangular to spherical coordinates. And then after that, I have to figure out, how I want to do this in terms of order of integration. And it doesn't really matter. We can try something, and if it doesn't work, then we can try something else. But let me just try d rho, d phi, d theta. See if this works. So theta can go from 0 to 2 pi. Moving one step inside, phi can be anywhere from 0 to arc cosine of 4/5. And then on the innermost integral, rho is allowed to go from 0 to 5. So this being my integrand, if I take the antiderivative with respect to rho, that's going to give me rho cube over 3. And so I'll take the 1/3 out as a constant. And so now I've got 0 to 2 pi of integral from 0 to arc cosine of 4/5 of now my antiderivative being rho cube sine phi, because we pretend that phi is constant, d phi d theta, lower bound 0, upper bound 5. So if I plug in rho is 0, 0 cubed is 0, and so everything goes to 0. So I need to think about what happens when rho is 5, and that would be 5 cubed sine phi. 5 cubed is 125. That's just a constant, so I can remove it. And then I would be left with sine phi. That's my new integrand. So let me write that a little bit lower. Get it away from the upper line. So this is 125 over 3, integral from 0 to 2 pi of integral from 0 to arc cosine of 4/5 of just sine phi d phi d theta. Now, you're right, the antiderivative of sine of phi with respect to phi is going to be negative cosine. Let me pull out the negative here, and then it'll just be cosine. And I'm evaluating this at arc cosine of 4/5 and 0. But actually, cosine of arc cosine of 4/5 is nice. That turns out to just be 4/5. So that's pretty good. That was pretty good in the end. So here we go. Integral 0 to 2 pi of 4/5 minus 1, because cosine of 0 is 1. D theta. So 4/5 minus 1 is going to be negative 1/5. And so I can pull out the negative and make that positive, and I can pull out the 5 and make that 3 times 5. Right? Okay. And so then my new integrand would just be 1, because I've pulled out all the constants, and there was only constants. And so if I take the antiderivative with respect to theta, then the antiderivative would just be theta, and I would take 2 pi minus 0, which is 2 pi. And so my answer in the end is 125 over 15 times 2 pi. So that would be 25 over, well, 50, I guess, because 25 times 2 is 50 over 3 times pi. 50 over 3 pi. So that's the volume of your ice cream.
It's not bad. It's just, I feel like if we mess up on one little thing.
Yeah, it's a long problem, isn't it? Okay. Any questions about this problem? Okay, so here we go. New problem.
The same.
This time, we are trying to find the center of mass.
Would a z-value of the center of mass, would it also be just, well, I guess first one integral z rho x, y, z?
Yeah.
dA.
Okay. Well, so there's two things that are really important. Is that yesterday we were using rho to indicate density. Right? Like the density of a planar lamina. But if we're going to use spherical coordinates, rho has to represent the distance away from the origin, right? And so just make sure, we're in this class, we use rho for two different things. Make sure you know what you're using rho for. And if you can avoid it, choose a different symbol for density than the kind of problem where we're doing this. In this problem, we're assuming uniform density. And so we're not even going to use rho to represent density. If it's uniform density, just pretend that the density is 1 everywhere. Okay? If you see the word uniform density, then that just means density is 1 everywhere. So this also reminds me of a mistake I made in lecture, I don't know if it was last time. No, it was, we were doing, okay, here it is. Here's my mistake. Are you ready to see my mistake? So exactly, yeah. You caught it. Yeah. So this formula for the center of mass, I was saying this to you guys, and I wasn't looking at the formula, so I forgot this. But there should be a little 1 over m here, indicating that you should take this integral and then divide by the mass to get your coordinates. And I apologize, that's my bad, but now you know. If you actually want the true coordinates, you have to divide by the mass. Okay, so we're talking about the same shape in this new example, right? We're just trying to find the center of mass now, not just the volume. And so if you were thinking about this shape, and I tell you that this has uniform density, so there's not any side that's more dense or less dense, there's not a side that's like heavier per unit volume, then you know that the center of mass has to lie along the z-axis, because there's no reason that it would lie more in the x direction or more in the y direction or more in the negative x direction or more in the negative y direction, right? It's got this radial symmetry. So the center of mass has to be on the z-axis somewhere, okay? So that's important. We know that just from symmetry. Symmetry has two M's. Symmetry. The x-coordinate of my center of mass is 0, and the y-coordinate of my center of mass is 0. So then that means for the z-coordinate of my center of mass, I have to use that formula 1 over m triple integral z, and normally we would multiply times like the density function, but like I just told you, the density is 1 everywhere. And so then we can just call it a day. So since my density is 1 everywhere, that means my mass is just going to be equal to my volume, right? So mass is basically equal to density times volume. And if you don't believe me, we normally think of mass as in like kilograms, if you're European anyways. So density would be kilograms per meter cube, and volumes would be in meter cube, right? So this checks out with my dimensions. As long as the density is uniform, you can do that. If the density is not uniform, then you've got to include it in your integral. But for us, we're going to use mass is equal to density times volume. So mass is equal to 1 times my volume. And I just found my volume in the previous question. It was 50/3 pi, right? Okay. So I can make that 3 over 50 pi to make it look nicer. Four now. And then I have this triple integral. I'm going to again convert to spherical coordinates. Z in spherical coordinates is the same thing as rho times cosine of phi. All right, so cosine of phi would be adjacent over hypotenuse. By multiplying by the hypotenuse, it only gives me the adjacent side. The adjacent side is my z coordinate. Okay, so that's the same thing as z. If I'm going to convert to spherical coordinates, I also pick up an additional rho squared sine of phi. And then I've got to decide on some order that I want to integrate this in. And so, I don't know. Really, you just choose something and you hope it works, and if it doesn't work, then you try something else. So let's try that order of integration. So, phi is allowed to be anything between 0 and the arc cosine of 4/5. Rho is allowed to be anywhere between 0 and 5. And theta is going to be anywhere between 0 and 2 pi. So this being my integrand, this is rho cube times sine phi cosine phi. I'm going to make a u substitution where u is sine phi, and that way du can be cosine phi d phi. Let's see how this turns out after that u substitution. So I still have rho cube. And then I've got the u from the sine phi. But then du is the cosine phi and the d phi, so I just write du d rho d theta. Oh yeah. Oh, so that's not very nice, is it? I think you're right. So if I draw a little right triangle, let's call it 3, 4, 5 triangle. So arc cosine of 4/5 would be this. That's my current upper bound. So if I take the sine of that angle, sine is opposite over hypotenuse, it should be 3/5. So Stephen is exactly right. My new upper bound should be 3/5. And then sine of 0 is 0, so I can leave the lower bound as 0. Yeah, good catch. So now the deal is, I take the antiderivative with respect to u, and it becomes rho cube u squared over 2. And then I pop in 0, which brings everything to 0, so that doesn't matter so much. And then I put in 3/5. Now I've got rho cube, and u squared is 9 over 25. So I'm just going to take the 9 over 25 and put it out here. D rho d theta. So we've got 27 over 2500 pi times integral from 0 to 2 pi. And now the antiderivative is rho to the 4th over 4, where we plug in 0 and 5. Obviously 0 doesn't matter. So if I bring out the 4, then that 2500 becomes 10,000. It's getting to be a really large denominator really fast. And rho to the 4th is now 5 to the 4th, which is it's 125 times 5, which is 625, I think. And there's no thetas, and so whenever I do this, it's just going to be multiplying by 2 pi, right? So this is 2 times 27 is 3 to the 3rd, and then we've got 10 to the 4th times 5 to the 4th. And then the pi's cancel. Pi in the numerator, pi in the denominator. Those pi's all cancel out. And
5 to the 4th is in the denominator, not in the numerator?
no, it's in the numerator. Yeah, thank you. Cool. So 10 to the 4th is just 2 to the 4th times 5 to the 4th. So I could also make that change. 2 over 2 to the 4th is just 2 to the 3rd, and then these 5 to the 4ths cancel. And then really, I get 3 to the 3rd over 2 to the 3rd, so that's 27 over 8. So 27 over 8, I like to do mixed numbers. So this would be 3 plus 3/8. And that should be the location of my center of mass, right? My center of mass in the XYZ coordinate should be 0, 0, and then 3.375. Really long calculation for this. But let's think if we made any mistakes or if this makes sense to us. 3.375 is like almost to where the cone intersects the sphere, so it's like up there somewhere where my cursor is of my mouse. That kind of makes sense for being the center of mass because the bottom part is really skinny, so it doesn't contribute very much mass. The top part is really heavy, so it should be closer to the top where my center of mass is. So I think that's it.